material. I think from one of the Coursera courses from I got it. That is, it is nothing but glorified prophecy. So that itself explains the relevance of our syllabus related to the new topic. So we know this is one of the slides which I like. Data never sleeps. So the rapid growth of the data. So everyone talks about data. Everywhere it is data. So data has become omnipresent, just like oxygen, maybe. And the satellite data is, we can see that it is that I mean, there is still no way to. I mean, that is the biggest that is a problem which everyone is facing. How to download, how to analyze, that it is uncountable. I can see. So I just it's an ASCOM data which I have taken from this. How the data spread has taken over the years. So I like this statement: data never sleeps. So that means our maths never sleeps. Then, then the new buzzword is big data. Big data. One, the data is big. We need to have uh, the reduction of data size. Time complexity has to be reduced. The space complexity has to be reduced, and optimization has to take place. From that, big data-driven decision has to be taken. Then that has to provide smart decision. That should ensure the smart decision making. The smart decision is a place where mathematics plays a role. Our properties plays a major role in all these analysis. It is not the calculation. It is our mathematical properties plays a role in this. Comes to data modeling. We know that it is there since age old years. It was through experiments, empirical data was developed, empirical data, then experiments, empirical relations, then conclusions, making the results, then theoretical, then there were many practices related to that. Then analytical models were developed, differential equations models were developed. Then comes to the computational models were developed. Then software related to it, numerical methods, optimization techniques, all related branches, then softwares related to that were developed. Then comes to the, so why do we need, then what is the role of mathematics? So a project or an experiment deals with one particular case study. We know that through the, so the, that is okay at a graduate level. But whenever we want to generalize, whenever we want to make a general theory related to it, we need to go for from a specific approach to a generalized approach. We have to go for a mathematical model. Only mathematical model will enable us to generalize the results that we all know. So that is why the need of mathematical model has come into existence. So, so mathematical model has not come into existence. We can say it has taken a different outfit, we can say. And also it provides you different tools, strategies, analysis, and the drawbacks, everything. So all the 5 days you all must be listening to the same thing I have taken from net, that is the real world problem, that is only real world problem, pose the problem statement, so then make suitable assumptions so that the problem can be solved, understand the constraints, simplify the constraints, identify the parameters, build an appropriate mathematical model, find the solution, analyze and interpret the solution, then again modify the model and make it modify so that it can take care of more constraints, it can be more suitable to imitate the real life problems. So this is all about in one slide I can say that's all about our mathematical model. So we can say in short, the maths or mathematical model acts like just like a compiler in a computer. Then comes to where this optimization models plays a role. Whether it is science or engineering, other than the theoretical work, wherever we have to go for, now it's a world of smart world. So whenever smart decision has to be done, or whenever the profit has to be done, profit, profit, that means less expensive, less time consuming, maximum benefit. All these are all optimization words. So all age-old optimization techniques will come into play, but in a new outfit. That's what I can say. Minimum. So then combining the optimization techniques in mathematical model, how it changed the MLDL techniques. That's what my next slides are talking about. Then comes to the goal of optimization. We know that we are dealing with maxima, minima, and the points of inflection since age-old days. Maximize, minimize, explore various methods or algorithm to obtain the best solutions, to achieve the best optimized solution, satisfying the various people, various constraints. So satisfying the various, so that phenomena, that the last slide you see the to provide the optimized best solution. So best, no one can define what is best. So that method will never end. So this procedure will, this technique will have that best is the, you know, it is like perfection. So that never ends. So always we have an option to go pursue research in this area and to develop more and more better solutions. Problem formulation. So I started with the the simple process of mathematical modeling. Why do we need optimization methods in modeling? What is the goal of optimization? What we are going to achieve out of it? Then what are the steps? So identify the problem parameters. So then identify the problem parameters. Along with that, we need to identify the influential parameters which affect the system. There are two types: influential parameters and the sensitive parameters. So these two has to be understood with the help of, by sitting with the expert from the field. We need to identify that. Then choose the, we can see the set up the variable bounds, create understand the bounds, choose the design variables along with the problem parameters, understand the design variable, list out the constraints or formulate the constraints, then formulate the constraints, modify the constraint as per the problem need require or as per the problem requirements. Sometimes we may have to convert an inequality constraint into an equality constraint, or we may have to modify the constraint. So to develop to for the need based solution, you adjust accordingly. Develop the mathematical model, analyze the solution, obtain the solution, analyze the solution, interpret the solution, improve the process. That I have not written here. Improve the process, create an iterative strategy, and create an epoch out of it. So a new word is EPOCH, that is iteration, a useful outcome-based iteration you need to create out of it. And continue the process till we reach the analysis. So again, our age-old numerical methods comes the starting the thinking of the initial approximation, how do you move from one step to the next step, the convergence criteria, how fast we will reach, and how the computational complexity of the problem. All these comes into play here also. Convergence, speed, accuracy, all those things again once iteration comes, all these ideas will also comes into existence. Only the terminology or the naming may be different. Then how to structure an optimization problem? We all know objective function, constraints, bounds, methodology. Methodology we need to, it's a collecting the data, decide the design variables, decide the objective functions and constraints, and decide the optimization techniques. Then here the collect the data. We know that. So everything, it's a database modeling, data-driven model. So everything depends upon how your data is noise-free. How good is your data? Decide the design variables. This you need to sit with a person, whosoever it is. It is an interdisciplinary area. You need to sit with the expert from the field, and based on the problem under consideration. Okay, so you need a problem expert, you need an expert from the field, you need a software person, you need a mathematician. So here, now designing the objective function, it is designing. Designing the objective function, it is not decide, it is designing. Designing the objective function and the constraints, here mathematician play a role. Then decide the approximation techniques, various softwares are available. Whether that software, whether the hidden techniques of underfitting, overfitting, error analysis, all those things are taken care. Which method gives you best results? Here again, role of mathematician plays a major role. Software may give you the result, but is that result appropriate? Is the method appropriate? So here we need to play a major role. So the third and fourth step, here we have to, this is major role where we have to understand the philosophy of the method, the accuracy of the method, whether we have to, the error analysis, underfitting, overfitting, etc. We need to understand mathematically and prove mathematically. So now comes to need of machine optimization ML or DL. So all the other branches, whether it is differential equation modeling, whether it is partial differential equations model, or our Lagrange's constraint optimization and constraint optimization, we know here. See the first here. Now the new era has come, the era of data-driven world, data-driven technology, data-driven method, machine learning, deep learning, artificial intelligence, smart learning. So here, this is one of the statement which I got. So sorry, just highlight the word machine learning in its most reduced form may be referred as glorified curve fitting. So this itself signifies the role of our syllabus, whether it is curve tracing, whether it is regression fit, whether it is a least square fit, whether it is an interpolation, whether it is a polynomial kind of any fit. What here, this is the in its core form, in its core definition. This material I got it from the Oxford website, from the Coursera, I think I have from the Coursera courses one by the, I think, Oxford University. Machine learning, its most reduced form, it is referred as glorified curve fitting. Curve fitting and the activation functions. These are the heart and brain of ML or DL. So both comes from, we call it as whether it is unit step function, whether it is sigmoid function, whether it is whether it is sigmoid function, logit function, or we can say that it is a this one by the 1 by 1 plus e raised to minus x, which we use in curve tracing. So all these functions, sign-in function, all these functions play a major role in starting from as an activation function to used in blockchain for even security aspects in blockchain. Whatever the curve tracing properties we are teaching in M2, so the asymptotic property, the significance of the tangent points, the finding out that then the points of inflection, all these points, all these concepts are very much useful in, they call it only we call it as curve tracing, we call it as activation functions, curve fitting we are covering. So in what we need to, I think it is just my opinion, we are not an expert from that field. So whatever we teach, but we need to provide a connection to the whatever the technique we are currently people are using. So that gives us that connection. That connection gives us the relevance of the topic, or we can understand it faster, grasper, and it will be more significant. That is just my perspective. So, otherwise, machine learning can be described as approximating a function. So that maps the examples of inputs to the examples of output. That is nothing but y equal to fx, fitting a data to a model. Fitting a data, so it's an algorithm which defines a parameterized mapping function. It's a weighted sum of inputs, just like our we can say that Ranjikuta fourth order method or any numerical method. It is nothing but a differential equation. We are solving nothing using a weighted approximation of a, we know that it's a weighted sum of the weighted averages. We use that method in solving the differential equation, all the Ranjikuta methods. The same concept is used here as well. So it defines a parameterized mapping function and an optimization algorithm to find the values of the parameters and the coefficient, and a continuous improvement strategy has been applied to it. And this is a concept which is being used even in neural differential equations. We know that ordinary is there, applied is there, a partial is there, then fractional is there. Now a new word has come, neural differential equations. So they use the same concept, weighted sum approach of the solutions. The optimization criteria should minimize the error function used to map the inputs to output in framing the problem as a function optimization. So whenever we fit a machine learning algorithm on a training data set, we are not solving a computer problem, we are solving an optimization problem mathematically, and the software and algorithm has been designed and coding has been generated by the software person. Now the goal is to I just have an example. So here, now is so I said that machine learning is a glorified word of curve fitting. Now, machine learning requires that machine learning or deep learning or artificial intelligence, it requires any smart decision making. So here it requires, we can see that they require maths. So most of the many courses they may require mathematics as a compiler. But computer is a branch which we can say starting from the data, any data analysis, any data, it requires optimization models or mathematical model. Starting from the initial stage, from the data collection stage itself. First is we need to collect the data, that is to remove the noise factor. Then from the data then first at the collection stage, that is we have to collect the data free from noise, and the data should be appropriate, it should be appropriate, it should be free from noise. Then comes to the classification. We know the age old regression techniques are one of the still popular techniques used in classification. Then comes prediction is also, it is nothing but we are getting a result of the form y equal to f. So at every stage, any machine learning algorithm, starting from data collection, data classification to data prediction, mathematics is used everywhere. So how it is being used? So here, the ability of the mathematics is not only software. How it is being used? So sometimes the prediction, it is like statistics. It depends upon the user. But here it plays a role, how much training data, how much the prediction is there. So there are two aspects, training and test. Training and test. So here, training and prediction here, what percentage of the data is used for training and what percentage of the data is used to obtain the prediction. So these two factors play a major role. Here, so every time they are trying to improve the accuracy by one second method may give 1% better results than the previous method. So here, the appropriate method should come from not through the software, through that mathematical equation or the mathematical equation that governs the mathematical model. So there may be errors like underfitting, like numerical methods. We talk about the truncation error, the round-off errors. Here also we need to make people understand about the underfitting, overfitting, how it occurs, what are the site conditions required for regression kind of analysis or gradient-based approaches, all these things to be, how much data is taken for test, how much data is taken for prediction, is that sufficient, will that give a good prediction? So all software may give you, one method may give you 85% result, other method may give you 87%. Why that method is giving, why 85, why the other method is giving 92? Here, the kind of equation what is used, the kind of mathematical equation used is a major role. So these are the underfitting, overfitting we need to stress on, and the kind of equations used for developing that model. Then the appropriate weights. The best results are achieved by using some optimization strategies, optimization equations, mathematical equations based on optimization strategies, which has been converted into algorithm and algorithm converted to optimizer, a software. So the way now optimization algorithms are responsible for reducing the losses and provide most accurate results as possible. And the weights are initialized by using some initialization strategies, and it is updated with each epoch. So that epo is a new word which we all should be aware of, and it's nothing but the outcome-based iteration we can see according to that equation. So I think, is it okay? Am I with you all? Uh, I think one person has raised the hand. Vidya Meshra. Is there any doubt? Hello? I think I can see one raised hand. Shall I? I think I can answer the question answer session after the presentation. Is that fine? Am I audible to all of you? Am I with you all?
Yes, ma'am.
Yeah.
Yes, ma'am.
Is the screen visible right now?
Yes, ma'am.
Okay. Yes. Okay. So that's all about the introduction, the need of the topic. So now we can see that machine learning models are typically founded on the principles of convergence, fitting data to the model. However, for now, some deep neural networks are the best possible solutions, and they also use optimization methods to arrive at the target. So fundamental optimization method used in ML or DL can be categorized into majorly into two categories: first order methods, higher order methods, and which, or I can further classify them into two parts: gradient based methods and gradient free methods. So my presentation is based on these two techniques: gradient based methods and gradient free methods. So let us start with the classical optimization methods. We know that constrained optimization, unconstrained optimization method, classical optimization method. It is available in the used in for finding maxima and minima. Analytical methods are used for finding the solutions. Some numerical techniques has been incorporated into it. Multivariable functions with constraints, single variable functions, multivariable optimization, single variable optimization, Lagrange's optimization, etc. So we know that limited scope of the here, all this requires differentiability condition that may create some problem for non-differentiable function. Then we have numerical methods, non-linear programming, linear programming, integer programming, usual operation research, linear programming, integer programming, quadratic programming, non-linear, I just listed a few, non-linear programming, stochastic, dynamic programming, etc. So we all know that when a linear, non-linear, integer, when we apply and what conditions it has been applied. So I just briefed them over here. Dynamic program, it is based on the splitting the problem into small groups. Stochastic, it is for random cases. Non-linear, when the constraints and design objective functions are non-linear functions, we use the non-linear programming, integer programming, etc. Then we come to bio-inspired methods, the evolutionary optimization techniques we call. So here, I told you, this is nothing but our Taylor series. If I say the whole this slide talks about nothing, the basis is nothing but our Taylor series method, I can say. Let it be a and call it, let it be a. There are two things. One is a search optimization technique, and other is gradient based optimization technique. Search optimization technique or graph theoretical algorithms are used, and the gradient based optimization techniques, it starts from our Taylor series method and the Newton's method. These are the basic foundation of any kind of these optimization techniques. Let it be an ant colony optimization, a swarm optimization, or a bat algorithm, or a firefly algorithm, a cuckoo search, a grey wolf, whale optimization, differential. I've just listed a few. So it requires, you need to know how the pattern takes place, the search algorithms, the pattern formation, That is a clustering the pattern formation, and the how the velocity. Certain algorithms are based on how fast it reaches velocity based algorithm, which is the Taylor's algorithm forms the basis for that. So these are just a word, but the mathematics behind it is nothing but, I told you these are the three methods. Depth search algorithm, breadth search algorithms, or distance-based algorithms, which is used in graph theoretical methods, pattern or clustering techniques, or Taylor series and Newton-based approaches. I just made a taxonomy of those classification: constraint, single objective, multi-objective, equalities, global, local minima, global minima, deterministic, stochastic, continuous, discrete. It is just a set of various different types of classification. So this classification will enable us to find out which optimization problem it has to be used for the type of problem which you are dealing with it. So before handling any type of the problem, we should have a general structure. So we should have a general table, optimization techniques, what kind of mathematical formulation is required, what are its strength and weakness, how fast it converges, what are the drawbacks of the method, and where it can be used, how it can be used. So this table is what we have to provide. Then what are the drawbacks and the advantages? So based on the problem, we should be able to tell, okay, this optimization problem may be suitable for this kind of problem, or this may be suitable for that kind of problem. So as a mathematician, we can say mathematically we should know, we should be able to list the kind of the optimization problems, and with its advantages, disadvantages, with its mathematical strength and weakness, and its properties, and how fast it converges, how it handles the underfitting, overfitting, and the errors. Now, some of these challenges, so this is just different kinds of optimization techniques. So starting from classical methods to the latest evolutionary optimization technique, I have listed a few. Now challenges. So we know that this is the, so here that is what we need to list with every kind of optimization techniques. What are its advantages, disadvantages? Where it can be used, where it successfully we can implement it, what are the drawbacks? So gradient information, like we know if the certain functions are non-differentiable, or certain functions may not be differentiable at certain points. So that in such kinds of cases, gradient algorithm cannot be used. So, now certain algorithm at the points of discontinuity, we may get stuck up with the local optimization. So that an algorithm should be, we will be stuck up with the local optimization. So we may not be able to reach the global optimization. So the method should be capable of handling that. Then nonlinear constraints, which I have discussed. Then multimodal functions, which we teach our students that functions may have many points of single discontinuities. So how do we multimodal function and multi-discontinuous function? How do we handle them? And what type of functions are there? How do we handle them? So what kind of optimization techniques can be applied to this? So here, to handle these challenges, any project person requires a scientist, or an engineer requires a mathematician. Then how to reduce the dimensionality reduction, computational efforts like FEM simulations may require high time. So how do we incorporate it mathematically? Then IoT based optimization, large data. So dimensionality reduction may play a major role. So what kind of algorithms may be used? Then whether the solution obtained is it robust? Will it change with the situations and circumstances? Or how can we obtain a robust solution? That is still a challenging task. Whether that's now, once we obtain the solution, is that solution is only a mathematical wonder, or is that solution really possible? So how to get a feasible, acceptable solution? So here, that is an interdisciplinary aspect. Okay. See, these are some of the challenges which I have listed. So now the mathematical concepts required. So that part is very easy. So I just took some problems of the optimization models. We all know that the finding the path, finding maximum minima. So look at the third picture. So they have written many one problem they have solved using many algorithm technique, stochastic gradient, adaptive gradient, Naster gradient approach. Many problem they have solved, and one problem they have applied many optimization technique, and they found that some and how the convergence takes place. They have analyzed through different paths, different colored curves are there. Actually, it is a simulation which I could not imitate over here. So, and they are saying which method is giving what kind of result they have given. So software can only give the results, the percentage. So that why that method is giving that much accuracy, there that only a mathematician can provide. That needs a lot of research, and we need to work on that heavily. It, by looking at the problem, or by looking sitting at one day and looking at the problem, it is not that simple. We need to. This is a good research area. So that requires the concepts are very simple. This requires only, now first is mathematical concepts required for gradient based optimization, gradient or Bayesian, steepest descent, conjugate gradient, Newton's method, and adaptive gradient. So these are the basic concepts required. We all know our gradient approach. Gradient, this is what we start our vector calculus. Bayesian. Bayesian, this can be added to a content beyond the syllabus. You can explain and the significance of Bayesian. The second order curves, the gradient is only used, can be used to first order approximation. Second order approximation, we may have to use the Bayesian approach. How Bayesian plays a major role, and the Bayesian matrix, this which matrix H happens to be a symmetric matrix, which can be used for orthogonal, which is used for singular value decomposition, orthogonalization strategies. So, and that will give a necessary support for all the conjugate gradient approaches and matrix decomposition techniques, because this and the stability analysis, because this matrix happens to be a symmetric matrix. And you know the reason why, which we teach our students from the first year itself. F of xi xj is same as f of xj xi in most of the cases. Then the only, I'm using this platform to tell that whatever we teach, only the wordings and the symbols are different, nothing else. That is the, I'm using this platform to explain that. This is nothing but downhill, uphill approach. So we know we use the same concept in numerical method, the same concept of, this is nothing but our directional derivative. Am I right? Del f dot a cap. That gives the del f dot a cap. If it is greater than 0, we can say that it is an increasing direction, it points uphill. If it's less than 0, it points downhill. So S transpose del f greater than 0 or less than 0, that tells us the direction of increasing direction, that gives us the search direction, which we are already covering in our directional derivatives. Now comes to the one theorem which we are starting from our first year M1, that is the Taylor series expansion. If I know the point and it's the speed at which the particle is moving, we can calculate the location of the points theoretically in the neighborhood region. The same concept is used, so that this is being used, this Taylor series expansion is one of this Taylor series expansion gives, this is the foundation for the branch of mathematics, that numerical method. Similarly, this Taylor's expansion gives rise to the concept for gradient based approaches. F of x plus h is equal to f of x plus h f dash x. This is for the, it is just a vector approach I have expressed it. So this Taylor series gives us the basis for all our search-based, velocity-based optimization techniques and the swarm-based optimization techniques. Or it can be gray wolf, how the wolf jumps, how the monkey-based the Taylor monkey optimization, which I will show in one paper how I used for a recent paper in International Journal of Numerical Methods in Engineering, how we use a Taylor monkey optimization, a hybrid optimization approach we use to solve one of the engineering problem. Gradient, Bayesian, uphill or downhill is nothing but our directional derivative. Taylor's expansion will tell us how to, with the velocity, how do we approach the next point. Search base, steepest descent with a quadratic approach. So this tells us, again here we use Newton's approximation. Xk plus 1 is equal to xk plus alpha s. Now, whether we should, here, one point we have to see is whether we should be going at search direction, how far we should go, or how do we understand whether the direction, point of inflection, whether there are any point of inflection, whether the direction changes or not, which we are explaining our students through our curve tracing in N2 and the numerical methods. Xk plus 1 is equal to xk plus alpha s. Only that direction concept is been added here. Then comes to the conjugate direction. So I told you that based on the Bayesian approach, Bayesian matrix, S transpose Hs, we get a quadratic form here. And by the conjugate direction theorem, we can calculate the optimal length, optimal step size, and all these topics can be or content beyond the syllabus or over and above. This leads to our conjugate gradient method. So, conjugate gradient method for higher order curves, the first order method may not be enough. So, we have to go to the second order approximation. Second approximation leads to what? Conjugate gradient methods. Conjugate gradient methods is conjugate gradient methods plays a major role in many of the learning algorithms. So there here also we calculated the optimal step size. Here through the approximation I'm calculating the conjugate, the optimal step size. Therefore the search direction is given by this, and the conjugate direction method, that formula conjugate gradient methods, it's available in the literature. So I've just copied from the textbook itself. So that formula gives us the here we can say some A transpose A. Here we can, this gives us the step size we can calculate from this. As a set of conjugate directions, there is an implicit, see, such kind of important property plays a role. If minimizing the line searches are used in along the conjugate directions, but the conjugate direction is guaranteed to minimize the quadratic function of n variables in n steps. So this indicates that the excellent convergent properties of Newton methods on general functions may be due to their conjugate direction properties than to their ability to approximate a Hessian inverse. So I just gave a sample problem to show how a conjugate gradient provides a function is given, starting conditions are given, gradient is given, how we are calculating the new search directions. Just a sample problem. So that's all about the unconstrained optimization. Constrained optimization, we know our Lagrange's method is there. So the Lagrange's method, till the Lagrange's function L of x lambda is equal to f of x minus sigma I vary from 1 to m lambda into gix minus bi. It provides the how the objective and binding constraints together. So this constrained optimization, if the objective functions and constraint functions are binded together in one function, and it provides you the trade-offs. We see that f of x plus lambda phi, the engineers or scientists talks about as the trade-off, the handshake or the trade-offs between the objective and constraint, how it balances each other, and the constraint function lambda I as the weighting factor. So try to add these terminology in our day-to-day lectures when we deliver the lecture. With its real meaning, of course. So I told you then again the another sentence which I got is all the impressive achievements of deep learning amount to just perfecting. And that is by Judy Upper. At the core of nearly all machine learning algorithm is an optimization algorithm. We all know that optimization algorithm is based on what optimization method. So again, I just quoted few of the statements world over. Hyperparameter optimization, best hyperparameter, model training, best model parameters, which I have covered already in my earlier session, data collection, that removing noise factor, training the data, test data, prediction, how do you reduce the dimensionality reduction, how do you identify the critical parameters, how do you understand the hyperparameters, how do we get the hyperplane? It's nothing but our linear algebra methods. Then we come to the, in short, I can say that the gradient. So this is one of the major category of the machine learning techniques. That is gradient methods. Gradient-based methods, whatever I was telling till now, it can be classified into three categories: gradient descent methods, stochastic gradient methods. There are many variations are there. Stochastic gradient method, mini batch stochastic gradient with momentum attached to it, NAC method, Nesterov accelerated gradient methods. Then comes to the conjugate gradient method. Conjugate, that is for a large scale linear system of equations and nonlinear optimization problems. Conjugate method gives you as the best solution. Then comes to the adaptive gradient method, that is ADA-grad. ADA-grad is still one of the it is nothing like, for a mathematician it is easy to understand. We use adaptive direction method in numerical methods. The same kind of philosophy is used in adaptive gradient methods also. So this gives you, adaptive gradient methods gives you a good convergence, a faster convergence as compared to the other method. So this is one of the most used ADA-grad methods are used in machine learning algorithms to get a good speed. So I think, is that is that okay? Am I with you all? Hello? Am I audible?
Yes, ma'am.
Yes,
Yes,
madam. Go
ma'am.
ahead.
Yes, ma'am.
Yes.
So that's about my first part. Second part is the screen visible? Yeah. Now we come to the gradient free methods. It's as simple as the whole, we can say the initial part of machine learning contributes to regression analysis. Our basic regression methods, it is not only used for prediction, it is used for classification as well. So the regression analysis provides the provides the basic fundamental to all machine learning algorithm in classification as well as prediction. So in a mathematical form, I'm expressing it like this, and logistic regression methods are there. Then we can say that the regression methods, but regression analysis, it is not, we can say that it is used for classification as well as prediction. It's depending on the all the independent variable. It's, we know the multilinear regression. Epsilon plays a major role. Beta I is the weighting factors. Input parameters xi must be linearly independent. Okay, so that the hidden conditions of regression techniques, how it is obtained, it is based on it's a best fit curve. We know that how the formula has arrived at it, so it can be generalized, easy to compute, it's easy to implement, but the only thing is the set of variables must be independent. So all the hidden conditions should be stressed upon. So along with the regression technique, where it is used, how it is used in classification, how it can be used in prediction, we need to explain. Now, most of the accident prediction or the binary type of algorithms, we use logistic regression. Logistic regression is nothing but fitting a curve of sigmoid function, which we fit the curve of, we remember, it is nothing but our sigmoid curve of curve tracing which we teach our students. The curve does not passes through the origin and the points of how the nature of the curve changes. F of x is equal to 1 by 1 plus e raised to minus x. The curve, the analysis of this curve explains the advantages, disadvantages, why it is being used, and all the properties of the curves are directly linked to the application of logistic regression and the inverse function, logit inverse. They may call it as logit function, we may call it as sigmoid function, f of x is equal to 1 by 1 plus e raised to minus x, and its inverse function. So this and how it is being used in maximum likelihood estimation, what is the role of what is the role of sigmoid function in logistic regression, how it is being used. So this gives the another binary category of the data we use. The most used regression technique is logistic regression, and if we can make our students understand the properties of these two functions, so the significances, I mean, we are playing our role. Then comes to the modified regression, lasso and ridge regression. These are just the big words. Lasso is nothing but a short form for least absolute shrinkage and selection operator. Least L, absolute shrinkage selection operator. Lasso. So I have to just look at the word absolute. Okay? Just look at the word absolute. So here, in some of the residual formula, the error factor, look at this, here modulus of AI has been used. Y equal to AX plus B plus absolute value has been used. That gives rise to our mean deviation and standard deviation. The same concept has been used here in LASSO. Modulus function has been used as a weighting factor. Lambda epsilon, lambda mod of AI has been used. Then ridge. Ridge regression, we use so the next approximation is what? The next approximation we can use it as sum of the squares. So the absolute square to reduce to nullify the error, we square the function or we take the modulus. So here if I take the square, we get a ridge regression. So lasso regression, here it coincides, look at the way, I just taken a simple graph, okay. It's large enough to find out the computational challenges. The tendency of overfit can be taken care. If the size of the data is less or less features, we can go with the ridge regression. If it is a smooth L2 regularization, we use a lasso kind of regression. And we need to think about the multicollinearity of the function has to be taken care. And look at how the sum of the squares plus epsilon, how the modulus value and the square value, how it changes. Look at how the smoothness changes, how the collinearity changes. Just look at the graph. That will tell us the advantage of lasso over the ridge. So, along with the formula, we need to understand when the lambda values are equal to 0, sum of the squares of both the methods equal to the ordinary least square method. So, the least square method has been least square method has been modified to include the epsilon value. So, one where modulus value has been taken, it has been named as lasso, and the other ridge. We have to go into the detailed analysis of it. So I just give you the overall aspect of it. So then, I have it is on International Journal of Numerical Methods in Engineering. That is the last year. I have published a paper with my colleagues with with our colleagues and to mathematics. We have a team in the college, so we made a paper related to hybrid multi-objective optimization using Taylor series and spider monkey optimization. So that paper, I have given this thing, so I can show you the paper, how what we have done in that paper if the time permits. So I think so. How the say day-to-day mathematics which we have covered in M1, the quadratic orthogonalization, quadratic functions, curve fit, which we teach in M1, and the curve tracing, what we teach in M2, and the optimization, Lagrange's optimization or maxima minima, and the regression techniques, least square method, curve fitting, normal standard curve fitting methods, regressions, and with some Jacobians, how it is being used in the advanced and the late, how it is being used extensively used in MLODL. I have presented in the last one. So I think I just give the overall framework, so which will provide you. I mean, all these materials are available in net. So I have taken from some Coursera material or from some websites or NPTEL or Coursera websites and from some learning materials or and some many from my research paper which I have used in for my publications which are while I was making our paper. So that's whatever I study that I try to put it in the most simplified form so that we can have a thought over it and how it can be used. So this was the aim of my lecture, and I just want to say that. So my again and again I am stressing that the machine learning or deep learning, we may have to. I think most of our colleagues we may have. I think many of our colleagues ask us, why do we need integration? Why do we need differentiation? The moment of inertia, what we teach in the integration, the area under a curve, what is the length of the curve, area under a curve, is being used for clustering techniques. So we may find it difficult how it is being used. Regression, the basic gradient, directional derivative. So it doesn't use any high fundamental maths. It starts from the simple Taylor series approach, Jacobian gradients, etc. That is what my that's what I would like to see. Again, I would like to end my session by saying that my the machine learning is nothing but a glorified curve fitting. Once again, that is what I mean. I was impressed with that statement. The justification I leave it to I mean, all my engineering maths colleagues and the other participants. But it is mathematical modeling is not a 5-minute job. It's not a So we have a major role to play. We need to understand it's a multidisciplinary field. Everyone has a role to play. Even we have a role to play. And our role is the it is not just a software part. The software may give you this is giving 95% accuracy, this is giving 92% accuracy, but why that method is giving 95 or 92%, or what modifications we can make to get a better improvement, or whether that method can be applied, whether are these variables linearly independent, whether inverse can be obtained, all these comes from deep mathematical knowledge. And here we have a major role to play. So any questions? I can show any questions. I can show my paper once I. Is that okay? Hello. I hope that you all are with me.
Yes, madam.
Any questions? Any questions? Okay, I'll just share my paper. Is it visible? Is this visible?
Yes, madam.
It's been published in 2020. It's a Taylor series model in spider monkey optimization. It's for used for optimization algorithm in wireless networks. The multi-objective model we developed, the proposed Taylor series model, algorithm is developed, cluster heads and local leaders have been taken care, global stochastic equiprobability has been, the estimation theory has been applied, and codes developed, it's a teamwork, so develop the algorithm, then through various methods it has been analyzed. A new method has been proposed. It's a resource, it has been used in wireless sensor networks as a resource allocation problem. So that's all from my side. Any questions? Is that fine? Prajakta ma'am? I hope,
Yes, ma'am.
so I think I end my session with we can have that code. Mathematical learning, machine learning is nothing but a glorified fitting, right?
Okay.
I'm ending with my code by Julia. I'm ending my session with that code. Thank you all. Thank you for patient listening. I hope I, this is what I want to convey to all of you. Just give a touch to that. Whatever the latest technology used, give a twist to it, give a touch to it, and work on it with your colors. Is it fine? Thank you. Thank you all. Thank you for patient listening.
Thank you, ma'am. 1 minute. Coach sir will join within 1 minute.
Yes.
1 minute, huh? हॅलो सर जॉईन करता का सेशन आमचं झालं आहे हां हां काही नाही तुम्ही एक 2 मिनटं वाटली तर बोला मी तुम्हाला हे करते रिक्वेस्ट करते हां कन्क्लुडिंगच सेशन आहे हां झाले सर सेशन मग आमचं शेवटचं होतं हां 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 Okay, good afternoon all. I request Dr. Suhas Khoth, Principal, KJ College of Engineering and Management Research, say few words on the occasion of concluding session of the IST approved 1 week STTP on applications of mathematical modeling in science and engineering. Over to you, sir.
Good afternoon to one and all. Am I audible?
Yes, sir.
Good, sir. Yes.
Okay, good afternoon to one and all. First of all, I thank Dr. Deshmukh Madam for conducting and taking initiative in having such a good 1 week IST approved STTP on application of mathematical modeling in science and engineering. Specifically, what I have seen up till now is many of the STTPs and FDPs are being conducted mostly on engineering related subjects. But specifically, we have conducted this particular STTP on mathematical modeling in science and engineering, related to engineering. And all the speakers, all the executive speakers, those who were called for this particular STTP, were of well known in their particular field. And the inauguration and keynote speech, I suppose, was given by Dr. Muzumdar sir. He is a chairman of BOS, SPPU, Pune, belonging to RSCOE. Then I think the second session was for Dr. Jatin, who is from ISPRIT. Then day 2 session was conducted by Professor Vishnu Tanpure from PICT. Then Dr. Bhatkar from MIT. And so many sessions were conducted up till now. And I was really amazed to see large number of participants also, those who have participated in this particular 1 week IST approved STTP. Today's session, I was just listening to Dr. Radhika Menon. It happens to be, we were colleagues long ago, Radhika Menon, if she remembers. And we had a very good time at D.Y. Patil College long ago.
Yes.
So, nice to see you, madam, after a long time.
Yes, same for me. Same.
Yes, yes.
It's always pleasure to share the session with you.
Yes. So I remember last week I requested her
Yes.
that yes, to conduct one session. And just I was in between, I was seeing when the session was going on. It was really a nice session and explained well. I think it was related to somewhere related to machine learning also. Why I couldn't make it out. So thanks, Radhika Menon, madam.
Thank you so much for inviting me. Thank you so much.
Yes.
It's always pleasure to work with you.
Yes. We have worked together
Yes, we had
for
a
many
great
years.
time together in yes.
Yes. So I request Deshmukh madam that all these speakers, all these distinguished speakers, we should have a file of all these speakers and let us have one more program, one more STTP, which will be related to specifically in science and engineering only. Only the subject related to it or domain can be changed and we can have a big workshop or STTP. And now, this time, Radhika madam, we are planning to have it offline.
Okay. That's great.
So that it can be benefited for majority number of staff members,
Yes.
and we can interact each other on a specific diet, right?
Yes.
So I request Deshmukh madam to have one more STTP again, and that will be offline in near future. And I thank all the participants, all the delegates, those who have participated in this particular STTP. I hope that they are being benefited through this STTP by one or the other reason, and I don't know how much percent, but definitely it would be helpful to them in near future. I can see many PhD scholars also, those who are doing PhD have attended the workshop. Many staff members have attended and given a very nice feedback also. I was getting some feedback also from the participants. So I thank all the participants, all the distinguished professors as well as staff, those who have participated in this STTP, and I wish that such type of STTPs would be conducted in near future by the department, and all should again participate in the next STTP, which will be offline. Thank you very much.
Thank you for inviting me for this workshop. Thank you, Coach Sir.
Okay.
And all my great appreciation to you and your team.
Yes.
Thank you so much.
Okay.
Thank you so much.
Thank you, sir. I request participants please share their views regarding STTP. Yes, anyone? Yes, anyone? Please share your views regarding this STTP.
Hello. Myself, Dr. S.S. Naik
Yes, sir.
from KK of Weather Engineering, Nashik. So I was a part of this session from last Friday, and all those speakers, they have done very good presentations, and the knowledge will help for all the participants who has given the importance of mathematics in science and engineering. Thank you very much.
Thank you, sir. Yes, anyone? Okay. I request all the participants please switch on your camera for taking photo. Please, I request all of you please switch on your camera. I request all Sanjay sir, Sukhdev sir, Naik sir. Okay, thank you.
Thank you, ma'am. May I leave?
Yes, ma'am.
Oh, thank you so
Thank
much.
you, ma'am. Thank you so much.
Thank you all, Night sir and all week.
Thank you, madam.
Welcome, sir. I can see everyone here. Thank you. Bye, sir. Bye, everyone.
ऐका ना, तुम्ही होस्ट आहात ना, मी तुम्हाला पण पाठवते. काय थांब ना, 2 मिनिटं थांब, मी सगळं बघते. थोडं हे होते. तू हे बंद केलं ना रेकॉर्डिंग?